Hello and welcome. So today we'll be working with some example elements that have D or F electrons involved. We'll be doing number 34, selenium. All right there you can see we have to go past the D block. And then we'll be working with number 82, lead. You can see we also have to go past the D block and even the F block, right? So those will be our two examples. We'll be doing some orbital diagrams, electron configurations, both the full and the condensed, and we'll be looking for those core electrons and those valence electrons. All right. But first, I think we need to talk about this question that comes up quite often. All right, and we foreshadowed this a little bit in the previous video. Why does the 4s orbital fill before the 3d when 3d, it's got a 3 in it, it's smaller? It seems to be the better choice. Why 4s before 3d when 3d is smaller? All right, and my answer to that, or perhaps nature's answer to that, is because 4s is actually a better choice at first. Okay. 4s is a better choice than 3d, at least at the beginning. All right, so I kind of drew this before and after picture to kind of put that in mind. And if you need the context again, all right, I'm talking about right here. Okay, I talked about Scandalous Scandium last time. So everything was all fine and good on the periodic table up until scandium. All right, so you can see with the beginning we had 1s, 2s, 2p, 3s, 3p, and like everything's good. Whether we're saying s or p, we just have the row number in front of it being equal to the number in front of the s or the p. All right, that row number being equal to our principal quantum number n. So everything's perfect. Okay, up until after calcium, 4s1, 4s2, and then scandium, it's 3d. It is not 4D, it's 3D. Okay, nature decided for this to be 3D, and we're stuck with that because that's from the mathematics of the Schrodinger equation, which is the equation describing how the electrons behave. So we're stuck with this being a 3, but there is a real-life answer to that, all right, which is getting here. Okay, that 3 in front of the D means it's a smaller orbital. Okay, so maybe that makes sense. Oh, the 3D is smaller, that's why I should have a 3 in front, because that number in front, the principal quantum number, has to deal with size. That is correct. But 4s is filled before any 3D. You go for scandium, you are at argon and you go 4s1, 4s2, and then 3d1. So here's why. When you don't have any d orbitals involved yet, 4s has room from the center of the nucleus all the way to the outside. Right? Oh, there we go. Now we're on the screen. Okay, we have room from the center of the nucleus all the way to the outside. Okay, this is, we could call this like a 90% probability radius. Basically, this is the orbital, right? And you can be anywhere here, including in or close to the nucleus, all right? If you go on to study more chemistry, you'll read, learn something about like orbital penetration, how deep the orbitals can go in the atom. And 4s has some of that orbital penetration going on. Said more simply, even though the 90% line is here, we can be basically anywhere in this region. Okay, so we got a lot of room to go, and you can have plenty of your space of the electron being around that nucleus, maximizing the attraction. All good things. But once we start adding some d electrons, they go into d orbitals. And the 4s electrons, that's not really too much of an issue for it, because they still have electron density, they still have the ability to go outside of the 3D region. All right, and so with that like flexibility, it's everything works out, and those 3D electrons can now just fill into those 5 different d orbitals that are closer, and those s electrons can stay on the outside. All right, and in fact, we're not going to do this in like this 101 course, but if we're to remove any electrons, those 4s electrons typically are knocked off first as they're on the outside. Okay, so the long story short, okay, especially at the 1-1 level, is just do it. Just do 4s and then do a 3D and just get used to that. And then after the 3D thing is over, you go back to 4p. 5s2, 4d10, 5p6, 6s2, 4f14, okay, 5d10, 6p6, so on and so forth. All right, so there's diagrams that exist, such as this. I pulled this from Wikipedia. I'll put the link in the description. And then you can see, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 3d, 4d, 5d, 6d. And here's like our row numbers. Row 1, 2, 3, 4, 5, 6, 7, also known as the period number. All right, and you can see that thing we talked about in the last video where the D's always one less than the row number. And here's the F block, rows 6 and 7. You can see F is always 2 less than the row number. Or you can print out something like this, where it's a little easier to see where the F falls into place. All right. 1, 2, 3, 4, 5, 6, 7. All right, and I'll put that link in the description as well. Again, I just got them from Wikipedia. Got some good stuff on Wikipedia. All right. So, we're almost ready to do the example. Like if it's for me, if I'm like trying to navigate the periodic table, I like to keep it pretty simple. I personally don't feel a need for like extra cheat sheets and stuff. I know that just scandium starts with 3D, cerium starts with 4F, and then I just kind of go from there. And for everything else, I just know S, P, D, F, and the row number. And I'm able to find everything pretty quickly. But I don't speak for everybody, so there are other techniques out there. And one of them is the so-called Madelung rule, also known as the diagonal rule. All right, and there's other names for this rule, but it's to kind of build a table like this and then look at things diagonally. So let me show you what I mean. So what I did in this table, I had to use a ruler here because my freehand's always not always so great. For this column, I have labeled 1, 2, 3, 4, 5, 6, 7 for my principal quantum number n. And then on the right here, I have labeling these columns S, P, D, F. All right, so rows are going to be n's, and then L's are going to be the columns. All right. And what you can do, okay, well, actually these get shaded out. And I guess that's one fair criticism of this technique, is you have to remember to shade those out. But some people like this. So you fill out, you just do matching, all right? So fast forward or skip this once you get the hang of it. So 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, F. G orbitals do exist, but I left that off there. We haven't discovered any elements with it, but if we were adding G here, there's even H and I, you would have that there. Practical purposes, we don't have to care about that. So that's enough. All right, so the diagonal rule is you build these diagonals. And for me, the hardest part of remembering this is like, where do I go with the diagonal? The answer is from top right to bottom left. All right, so we're going to kind of go here. Let's. Ooh, how do I visualize this without like disrupting it too much? So we'll try maybe green. We'll go with green and red. Those are contrast colors. So we go through 1s. I'll just stick with green. We'll just dot, dot, dot. Oh, dot right here. Sound effects are optional. Oops. Okay. Something like that. All right. The periodic table actually, as we know it, stops at 7p, so I'm just going to cross that out. We don't need that anymore. Okay. And so using the diagonal going in this direction, you can see that I went 1s, 2s, 2p, 3s, 3p, 4s, 3d, and see, it using this technique, it got the 3D correct. Okay, instead of it being like a 4D, you looped around, we went 4D. Okay, and then we went 4P. All right, so if you're like wondering, where does a period end, a row end? It always ends with the P, except if you're in the 1s. Okay, so that's like kind of the end of your row. All right. Yeah, so 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, nope, 4f. Okay, and then 5d, 6p, 7s, 5f, 6d, 7p. All right, we did it. So it captures that order correctly. All right, so some people love this. All right, you saw me kind of struggle through that. That was probably the best take I'm going to get, so I'm not going to refilm that. But in my mind, I kind of think here. All right, I have these silly mnemonic devices. This is almost a haiku, so I put like haiku-ish. Scandalous Scandium. We live in a 3D world. 4 starts with F. All right, so here's Scandalous Scandium, 3D. We're living in a 3D world. All right, cerium. There's cerium. Starting with F starts with 4. All right, and so that's the way I like to remember that. All right, and one more thing. First appearance of S is 1s. First appearance of P is 2P. First appearance of D is 3D. First appearance of F is 4F. That's just part of the mathematics of Schrodinger's equation. All right, so we're stuck with those. And those first times are for hydrogen, boron, scandium, and cerium. All right, so I find this easier, but if you like this, go for it. All right, so with that out of the way, now that we know how to navigate the periodic table, we can finally get to some examples. So for today, we have selenium and lead. Let's start with selenium. All right, example 1 for selenium, please give the following. Please give orbital diagrams, full and condensed. Give electron configurations, full and condensed. Show the core electrons and the valence electrons in each of the diagrams and configurations. All right, so we got a little bit of work cut out. Here we go. Selenium is number 34 on the periodic table. Okay, so in its neutral state, ions will be a different video. We're doing neutral stuff today. So for neutral selenium, 34 protons, 34 electrons. All right, so let's go ahead and do this. Okay, I like to just follow the periodic table at first. So we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, 2, 3, 4. Okay, 4p4. And then we're going to end at 4p4. We don't go all the way to 6 because that would be krypton. All right. So I like to do orbital diagrams first. Now that's a slight lie. When I'm teaching, I like to teach it first, but in reality, I actually do like to do the electron configuration first. I'm not going to lie about that anymore. So let me go ahead and be the truthful version of myself. I'm going to do the full electron configuration first. All right, so here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4. Okay. 1, 2, 3, 4. Yeah, got that done. All right, and you can always feel free to check your work. All of the exponents, those are just number of electrons in these individual subshells. All right, and those should add up to 34. 2 plus 2 is 4, 10, 12, 18, 20, 30, 34. All right, so that is good. All right, let's do the condensed electron configuration next. All right, I know someone's going to be driven nuts by me forgetting that colon. So there we go. All right, so condensed electron configuration. Let's work backwards to find the most recently filled noble gas. And that looks like it's going to be argon at 18. We can just confirm going backwards, 34, 33, 32, 21, 20, 19, 18. We have argon. All right. So argon stops at 3p6. And then we can just drop those down. All right, that's done. All right, before we do the orbital diagrams, I think it would be good to point out the core versus valence electrons. All right, so core electrons are, valence electrons are any electrons you have in the highest principal quantum number, highest n. So as I go through this, I'm looking for what's my highest n? And the answer, is it 1? No. 2? No. 3? No. Sounding a little bit like reading a children's book right now. No. And then, but we got 4. All right, so we got 4s2, 4p4. So right here would be our valence electrons. Now notice I did not include the 3d10. As we explained before, those 3d electrons are closer to the nucleus, which means they're not valence electrons, all right? You're like, well, it filled like in between these valence electrons. Yeah, but it's smaller. It's got a lower n value, which means they're going to be held too tightly to do any chemistry with, right? So highest n, you'll be boom, boom. Okay. Now, like I said in the last video, I'll do it again. I think it's great to go to your periodic table and just write 1, 2, 3, 4, 5, 6, 7, 8 valence electrons above those main group columns, main group meaning S and P blocks immediately, right? I always encourage doing that. And of course, in this context, helium actually belongs here in the S block, not with the P block. All right, so yeah, does it check our quick cheat sheet here? Yeah, it does. It's in the 6 valence electron column. So I really encourage you, especially in a homework exam situation, write this out. The common answer, I would guess the most common wrong answer for selenium for the number of valence electrons, I would guess someone would just go, and you'd be like, oh, 2 plus 10 plus 4, and go 16. But that's not it, okay? And if you're like, well, I need proof, you study selenium chemistry, and it's consistent with an element that has 6 valence electrons, like a sulfur, like an oxygen, right? They all behave very similarly. So it's not 16, it's 6. All right. So here's my valence electrons. I'm using green here. Okay, or I like to write that VE minus. And if we're counting the number of valence electrons, we'd have 6 valence electrons in selenium. All right, which means everything else is a core. So I'll use red here. That's core, that's core, that's core, that's core. All right, 18 plus 10 is 28. Okay, so we have 28 core electrons. Okay. All right, 18 there plus 10, or you can count the 18 here individually plus 10, that's 28. Okay, and the core plus valence would add up to our total number of electrons when we're discussing a main group element into S or P blocks, which is what, at least what I teach in 101. Okay. All right, let's move on to the orbital diagrams. So even though I like to teach orbital diagrams first, before electron configurations, I find it easier to do this because it gives the easy template for setting up the orbitals in the orbital diagram. You'll hopefully see what I mean. So I know I did boxes in the last video. Just to save time, I'm just going to stick with, I'm going to do spaces this time. All right, so 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Looks like I ate up my room for the condensed orbital diagram. I'll just like squeeze that right here. Okay. We'll do that last. All right, so here we go. 1, 2, we have to go to 34. 3, 4, 5, 6, 7, 8, 9, 10, 12, 18, 20, 30, 31, 32, 33, 34. All right, there it is, selenium. Condensed electron configuration would be realizing that everything between here and here is just an argon. Okay, like we did there, just using your previous noble gas, and it must be a noble gas for the reasons we explained earlier. All right, and then I just got to write out that part. 4s, 3d, 4p, and so we have the remaining 16 to write out. 1, 2, Okay, we're at 12, got these 10 done. We have 4 left. Basically, I just copy and pasted that here, okay? And then there's our condensed configuration, all right? I'll point out the core versus valence, all right? So with red, I'll do a box for core. And then I'll do green circles for valence. All right, there we go. There is selenium. Done. Okay, last example for this video, we'll be doing lead. This one will take longer. There's 82 electrons. All right, there it is, lead, 82. All right, so let's narrate its electron configuration. Here we go. 1s2, 2s2, 2p6, 3s2, 11, 12, 13, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p2. All right, that's a lot. All right, so we had 82 protons, 82 electrons, full electron configuration. All right, there we go. Okay. And I'll just do this. I don't always do this, but I'm just giving you a sense of the period numbers, the row numbers. Row 1, okay, row 2, row 3, row 4. I guess the technical term is period P, but I've been using R's already. R5, R6. Okay. Yeah. Okay. Let's just make sure our D's are always one number less than the P's. Good. Good. S and the P's, I mean. And then let me make sure that my F's are 2 less than my S and P's. And that is good. All right, so that's done, and then we can do a condensed. All right, so a noble gas, unless it's helium, always ends in a P6 of some flavor. So we're just here, we go backwards. So 5p6, that should be row 5, that should be xenon. If you don't believe me, just count backwards. To a noble gas. 82, 81, 72, 71, 57, 56, 55, 54, xenon. And then we just drop that down. All right, we'll do the orbital diagrams. Next, let's just do those valence and core electrons. Highest N is 4, or excuse me, 6. And so we're looking here and here, right? So those would be our valence electrons. And if we were counting, oh, did I write? That should be a 2. 6s2, 6p2. Those are our valence electrons. And if we were counting our number of valence electrons, it'd be that 2 plus that 2. 2 plus 2 equals 4 would be our number of valence electrons. All right. And does that hold up with our periodic table cheat sheet? There's lead. It's in the 4 column. We are good. All right. So you may be wondering, well, lead, it's got 82 electrons. You're saying out of 82, 4 that's the only number really involved in chemistry? Yep. So you have 78 charge balancing filler electrons. Not to say they're not important, okay? Yeah, lead with 82 electrons can be boiled down to what are those 4 electrons doing? All right. There they are in the condensed configuration. And then core electrons would be everything else. Okay, all that's core, and then those are core as well. Same deal here. So that'd be our number of core electrons would be 78 electrons. Okay. Just labeling everything. 4 electron. Yeah. Okay. And 78 plus 4, 82. Yeah, we got it. All right. So that's the electron configuration. And now let's do the orbital diagram. Here we go. Let me show a different way of doing an orbital diagram. It's like a vertical style. So we would have our nucleus right here, 82 protons, okay? And, you know, if we're building up, here's a Bohr model as an example. If we're building up layers of our atom, the electron shells like 1s, 2s, 2p, and then you have the 3s, you know, so on and so forth. You know, 4p keeps getting like wider and wider and wider each orbital, right? Which means that the orbital is going to have more distance. As we increase our orbitals, they're going to have more distance away from the nucleus. So I like to show that in a vertical way sometimes, and some textbooks will too. All right. So we'll just, instead of going horizontally, we're going to go vertically. So we have 1s, 2s, ran out of room, huh? All right. And we'll try that again. Whew, all right. Barely. All right. I know this is a lot. Me personally, on an exam, I don't know if I would ask a student to do this much. In a full form, I would probably just ask for like a condensed orbital diagram. But I'm a believer that classwork, homework, studying should be done at a harder level than the actual thing. So here's the full thing. Now I'll use the orange this time. All right, we gotta go 82 times. 12, 18, 20, 30, 36, 38, 48, 54. That's a good point to make a check, okay, because that was our previous noble gas. All that was equal to xenon. Yeah, all right, we're doing all right. So 54, and then we have to go up to 82. So 55, 56. 70, 80. All right. And to use using an analogy of like landing an airplane, here I'll just kind of cruise in. Once you get to the previous noble gas, that's when, if you were to be a pilot, you like start your descent. You have to like, all right, I gotta be a little careful now. And especially here, the last electron, that's where you're sticking your landing. We have 2 left to go. And, you know, double check you didn't pair it up, right? They shouldn't be paired up until they must. All right, so 81, 82. And there we go. Okay, that would be the full orbital diagram. Okay. If you were doing a condensed electron, a condensed orbital diagram, you would just write xenon to represent all of that, and then you would write out that. All right. Just for the sake of being complete, I will capture that on video. All right, we're at 54 with xenon, so we have to hit 82. 55, 56. 70. 80, 81, 82. Core. Core. Valence. Okay, 4 valence electrons. All right, so that's it for this video. Closing thought, I've had a student ask me a few times over the years, if these are actually closer to the nucleus, then how come they are in between the two valence distances? And the answer is, in reality, they should be lower, and they are. But we like to write our diagrams this way because it shows the order of filling. Okay, so similar phenomenon with like when f orbitals are involved. Like I said in the beginning, you can have. Man, I got so many papers. But it's going to be a similar situation to here, that even though like 3D fills after 4S, it is still in reality smaller. All right, so just trust the order and you'll be okay. All right, thanks. Take care.